Hello, welcome back to the series of lectures on molecular spectroscopy in the Department of Chemistry, University of Lagos. In this series, we're going to talk about vibrational spectroscopy and in particular IR spectroscopy of diatomic molecules. A vibrational motion is a periodic motion about an equilibrium point. It's something that we are all familiar with, a gyration about an equilibrium point. In a molecule, we say that there's a pure vibration when the atoms in the molecule are in periodic motion. So periodic motion, that's a oscillatory motion, while the molecule as a whole has constant translational, rotational, and electronic motion, meaning that the translational motion, that's the motion in discrete time, is constant, the rotational is constant, and there are no electronic transitions. Then we say that we have a pure molecular vibration. There are two major types of molecular vibrations. There's the stretching of bonds. Sorry about that. So there's the stretching of bonds, and then there's bending of angles. Those are all other types are grouped under this. So we can study vibration in molecules using the IR technique. The IR technique studies the absorption and emission of light in the IR, this picture is a little tiny, is in the IR region of the electromagnetic spectrum. Remember, the electromagnetic spectrum contains light of various frequencies, and they are dependent on the interaction that they have with the molecule. The other type is Raman scattering. Raman uses a laser light to study the different vibrational levels in a molecule. However, Raman can also be used to study other types of spectroscopy, like rotational and electronic spectroscopy. So each fundamental type of vibration in a molecule, like this bond stretching, is called a normal mode or a vibrational mode. So this is another example of a normal mode. So this is a symmetric stretching of the bonds in the water molecule. It's another example. That's the symmetric bending of the angle in the water molecule. And then the last one, this is an out of plane vibration, so it's also a normal mode. So any type of vibration is called a normal mode. So in a molecule that has n atoms, for example, benzene has 12 atoms, the total number of degrees of freedom, motional degrees of freedom, that's the ways in which the molecule can absorb energy, is 3n. 3 of these belong to translation, whether it's a linear or a non-linear molecule. If it's a linear molecule, like carbon dioxide, yes, the rotational mode has 2 degrees of motion, and then the remaining 3n minus 5 is for all the normal modes, that's the vibrational motion of the molecule. If it's a non-linear molecule, again, the total is 3n, 3 goes to translation, but in this case 3 goes to rotation, and then we have 3n minus 6 for vibration. So a diatomic molecule which has n equals to will only have 1. The normal modes of vibration of polyatomic molecules are independent of each other, meaning that the vibration of one does not affect the other. So for example, is the vibrational modes, which are the normal modes, for CO2, so we have to determine CO2, H2S, and C2H6. It's important to know the shapes of the molecule. So for CO2, there are 3 atoms, 1 carbon atom, 2 oxygen atoms, and we know that the molecule is linear. So the number of vibrational modes will be 3n minus 5. N is 3, so we substitute 3 into that, then we have 3 into 3, that's 9 minus 5, that's equal to 4. H2S is a non-linear molecule, it's a bent molecule, so the number of vibrational modes will be 3n minus 6. That's the formula for non-linear molecule, and we have the same thing for benzene, 3n minus 6. So for the H2S, it's also 3. The number of atoms, 2 atoms of hydrogen and 1 atom of sulfur. 3 into 3 minus 6, that's 3 times 3, 9, minus 6, 3. So the linear molecule has more vibrational modes than the non-linear molecule. So then we have this, the benzene molecule. The molecule is non-linear. There are 12 atoms, 6 carbon atoms, 6 hydrogen atoms, and then we have 3 into 12, that's 36 minus 6. The general selection rule for a molecule to be observed in a vibrational spectroscopy is that the molecule must have a dynamic dipole moment. A dynamic dipole moment is there's a dipole that changes with vibration. So the dipole either changes in magnitude or in direction. You know, a dipole is a vector quantity that talks about the charge separation in the molecule. So let's consider the carbon dioxide molecule. The carbon dioxide is a molecule that has 0 dipole moment. If we now consider, there's several vibrational modes in this molecule. The bonds, remember we said they're bond stretching, so let's look at the bonds stretching together. So this is the bond stretching out, the two bonds stretch out simultaneously and compress simultaneously. The dipole moment is still 0 because it cancels out. In such a situation, this is not observed in IR spectroscopy. This vibrational stretch is not observed in vibrational spectroscopy. Now consider a situation where carbon goes up and the 2 oxygen comes down. So if we liken this to our SO2 molecule, the dipole moment is not equal to 0 in this case. So this vibrational motion changes the dipole moment, changes the magnitude of the dipole moment. So this vibrational motion is IR active. We consider this asymmetric stretching as well. So that's one bond compressing and the other bond elongating. If you look at this structure, it's obvious that the dipole moment is also not 0. So this mode, vibrational mode, will be IR active. For diatomic molecules that have just 2 atoms, so a diatomic molecule, this is a homonuclear diatomic molecule. For all homonuclear diatomic molecules, the dipole moment is 0. So the only motion that they can have is to stretch it. So if we stretch it, the dipole moment still remains 0. For heteronuclear diatomic molecules, the dipole moment is not 0. So a bond stretching will change the magnitude of the dipole moment, since mu is proportional to the distance between the 2 charges. So a diatomic molecule must be polar to be observed in IR spectroscopy. However, a polyatomic molecule, like the carbon monoxide, need not be polar. In the next video, we will talk about the theory of vibration.